Hello and welcome. Tonight we are going to follow 10 moments when space reached down and touched Earth. Some of these events were quiet, some were strange, some were beautiful, some were frightening. A few left only stones in fields, rooftops, deserts, and forests. Others lit the sky brighter than the sun. Shattered windows, carved small craters, or flattened trees across enormous areas. This is not a countdown of the largest impacts in Earth's entire history. If we counted all of geological time, the list would belong to ancient giants, impacts that happened millions or billions of years before cities, writing, or human witnesses. The Chicxulub impact, for example, helped end the age of the dinosaurs, but it happened long before recorded history. Tonight, we are staying closer to the human story. These are 10 famous space rocks that struck Earth, exploded in the atmosphere, or rained fragments onto the ground during recorded history or in modern documented times. Some were asteroids, some were meteoroids. Some became meteors, the bright streaks or fireballs we see in the sky. Some survived as meteorites, pieces of space rock that reached the ground. And some never made a crater at all because they exploded high in the atmosphere as airbursts. That is one of the most important things to understand. A space rock does not need to hit the ground to be dangerous. The atmosphere protects us from countless small objects every day. Tiny grains burn up as harmless meteors. Larger objects can fragment and explode. But when a space rock is large enough, fast enough, and strong enough, the atmosphere does not simply erase it. It turns its energy into light, heat, pressure, and shock waves. A crater is not the only mark a cosmic visitor can leave. Sometimes the mark is broken glass. Sometimes it is a bruised human body. Sometimes it is a fresh hole in the ground. Sometimes it is a forest lying flat in every direction. And sometimes it is only a lesson that Earth is not separate from space. It is part of space. It moves through a solar system filled with dust, stones, iron, ice, and ancient fragments left over from the birth of planets. Most of the time, the sky is calm, but not always. So let us begin at number 10. Number 10 is the Ensisheim meteorite. In the year 1492, long before modern astronomy, long before people fully accepted that stones could fall from space, a large meteorite came down near the town of Ensisheim in what is now France. People saw a fireball. They heard a great sound. Then a stone was found in a wheat field. The meteorite weighed about 127 kilograms when it fell, and it became one of the most famous recorded meteorite falls in Europe. It is often described as the oldest preserved European stony meteorite fall with a known date, and pieces of it still survive today. To modern science, this was not a world-ending event. It did not destroy a city. It did not flatten a forest. It did not leave a massive crater. But historically, it was remarkable because people were forced to confront something that seemed almost impossible at the time. A stone had fallen from the sky. Today, that sounds normal. We know meteorites exist. We know Earth is struck by material from space. But in 1492, the idea that rocks could fall from the heavens was deeply strange. Some people interpreted the event as a sign or omen. Others took fragments. The stone became a physical object caught between religion, politics, superstition, and early natural science. The danger from Ensisheim was local. If a stone of that size had landed on a person, a house, or a crowded street, it could have killed. But it was not a civilization-scale threat. It was too small for that. It mattered less because of what it destroyed, and more because of what it revealed. Earth was being hit from above, not symbolically, not mythologically, physically. A real stone from space had crossed the atmosphere, survived the fire of entry, and landed in a human field. Imagine a village in the late 15th century. The sky is not yet understood as space in the modern sense. There are no satellites, no spectrometers, no orbital calculations, no asteroid surveys. Then the day is interrupted by thunder from a clear sky, a falling fire, and a stone too strange to be ordinary. It would not feel like science at first. It would feel like a message. But now we know it was not a message. It was a fragment of the solar system. A piece of ancient material, traveling silently for ages, until Earth crossed its path. Number 10 reminds us that the story of impacts is also the story of how humans learned that the sky is not untouchable. The heavens can fall. Number 9 is the Murchison meteorite. On September 28, 1969, a meteor broke apart over the town of Murchison in Australia. Fragments fell to the ground, and people collected pieces of a dark, carbon-rich meteorite that would become one of the most scientifically important meteorites ever studied. Murchison did not destroy a city, it did not kill anyone, it did not leave a huge scar in the landscape, but scientifically it was extraordinary. The meteorite contained a rich collection of organic compounds, including amino acids. Later studies identified many different organic molecules, some with clear extraterrestrial signatures. The Murchison meteorite helped show that some of the chemical ingredients associated with life can form in space or in small parent bodies in the early solar system. This makes Murchison a different kind of impact story, not a story of destruction, a story of delivery. Space rocks are often imagined only as threats, falling mountains, city killers, dinosaur-ending disasters. And sometimes they are threats. But they may also have played a constructive role in Earth's history. Meteorites and comets may have delivered water, carbon compounds, and other materials to the early Earth. They did not create life by themselves, but they may have enriched the young planet with useful chemistry. Murchison is a reminder that space rocks are not only weapons of nature, they are archives, they are time capsules. They carry material from the early solar system, often older than Earth itself. The Murchison meteorite is a carbonaceous chondrite, one of the more primitive types of meteorite. Such objects preserve clues about the chemistry present when the planets were forming. Studying them is like reading a chemical memory from more than 4.5 billion years ago. If a Murchison-sized fall happened over a town, the danger would mostly come from individual fragments. A person could be struck, a roof could be damaged, a car could be hit. But the greater significance would still be scientific. The object was not large enough to threaten humanity. It was large enough to bring cosmic chemistry to Earth. And that contrast matters. Not every visitor from space is a disaster. Some arrive as quiet messengers from the beginning. In a top 10 list of space rocks, Murchison earns its place not because it shook the world physically, but because it changed the questions scientists could ask. Could the building blocks of life exist beyond Earth? Could organic chemistry be widespread in the solar system? Could meteorites have helped prepare the early Earth for biology? Murchison did not end life. It helped us wonder how life began. Number 8 is the Peekskill meteorite. On October 9, 1992, a bright fireball crossed the sky over the eastern United States. It was seen by many people and captured on several videos, which made it one of the most famous filmed meteor events of its time. Then, one surviving fragment reached the ground in Peekskill, New York. It struck a parked car. The car belonged to Michelle Knapp. The meteorite punched through the rear of her 1980 Chevy Malibu. The rock weighed about 12 kilograms, and fortunately, the car was unoccupied. No one was killed, no city was damaged, but the event became famous because it connected cosmic impact with ordinary life in such a direct and almost absurd way. A space rock crossed interplanetary space, entered Earth's atmosphere, survived the fireball, fell through the sky, and hit a car. It sounds like a scene written to be unbelievable. But it happened. Peekskill is important because it makes the risk personal. A Tunguska-sized event feels huge and remote. A dinosaur-killing asteroid feels ancient and almost mythological. But a meteorite hitting a car in a driveway feels close. It reminds us that most impacts are not extinction events. They are small, random, local, and strange. A rock does not need to be enormous to change a person's day forever. The Peekskill meteorite also helped scientists because the fireball was filmed from multiple locations. Those videos made it possible to reconstruct parts of the object's path through the atmosphere. Modern meteor science often depends on exactly this: cameras, dash cams, security footage, satellites, radar, and networks of observers capturing fireballs from different angles. Today, a similar event would probably be recorded by dozens or hundreds of phones. In 1992, the fact that the fireball was captured on video was already remarkable. What if Peekskill had been larger? A 12-kilogram surviving fragment is dangerous to a car, a roof, or a person. But the original object was still small compared with the events higher on this list. If the meteoroid had been tens of meters wide instead, the story could have resembled Chelyabinsk, with an atmospheric explosion and shockwave. If it had been iron-rich and strong, more large fragments might have survived. If it had fallen over a dense city, many smaller impacts could have damaged buildings or injured people. But as it happened, Peekskill became a rare kind of cosmic accident, not apocalyptic. Almost intimate, a private property claim from outer space, a reminder that Earth is struck not only in deserts and forests, but sometimes in driveways. On November 30, 1954, in Sylacauga, Alabama, Ann Hodges was resting on her couch when a meteorite crashed through the roof of her house. It struck a radio, bounced, and hit her, leaving a large bruise. She survived. But she became famous as the first well-documented person known to have been struck by a meteorite and survived. This event was not large on the scale of planetary defense. It did not make a crater. It did not shatter a town. It did not start fires or break windows across a region. But emotionally, it is one of the most striking meteorite stories ever recorded. The odds of being hit by a meteorite are incredibly low. Most meteorites fall into oceans, deserts, forests, fields, or unpopulated regions. Earth is wide, and people occupy only a small part of its surface. Even when meteorites fall near towns, they usually land harmlessly. But in 1954, one fragment found a roof, then a radio, then a person. It is the kind of event that makes statistics feel personal. Ann Hodges' story also shows the social aftermath of meteorite falls. The object became the center of attention. Crowds, reporters, legal questions, ownership disputes, and public fascination followed. The meteorite was not only a scientific specimen. It became a human story, a legal story, a media story. A small rock from space entered a private home and disrupted an ordinary life. That is one of the strange things about meteorites. They belong to no one while they travel through space. Then they land on Earth, and suddenly they belong to geology, law, museums, collectors, science, and sometimes human drama. Could a Sylacauga-type event be very bad for humanity? No, not by itself. But it shows a different category of risk, direct impact by a surviving meteorite fragment. These are usually small and rare, but they can damage roofs, vehicles, and people. A larger fragment could kill. A shower of fragments over a town could cause more serious damage. Yet compared with airbursts and larger asteroids, the danger is localized. Still, Sylacauga is unforgettable because it brings the cosmic scale down to one room. A woman rests on a couch. A rock older than Earth breaks through the ceiling. The universe enters the house. Number 6 is Sutter's Mill. On April 22, 2012, a small asteroid entered Earth's atmosphere over California and exploded in the sky. Fragments fell near the historic Sutter's Mill region, the same name associated with the California gold rush. This fall was scientifically valuable because the meteorites were carbonaceous chondrites, fragile and primitive material from the early solar system. Some fragments were recovered quickly, before rain could heavily alter them, allowing scientists to study delicate minerals and chemistry from the parent body. NASA's astrobiology program later highlighted research on Sutter's Mill samples, including what they revealed about the meteorite's composition and alteration history. Sutter's Mill was not a disaster, but it was a warning in a soft voice. The incoming object released energy in the atmosphere. It broke apart. It scattered fragments. It showed again that Earth is constantly receiving material from space, and that even small incoming bodies can produce bright fireballs and detectable shock waves. If a Sutter's Mill-type object had entered over a major city, the result still would not have been like Tunguska or Chelyabinsk unless the object were larger. But people might have heard sonic booms. Small fragments might have hit roofs, cars, roads, or fields. The main impact would have been attention, not devastation. Scientifically, however, such falls are treasures. Fast recovery matters because meteorites are altered by Earth's environment. Rain, soil, oxygen, microbes, and handling can change the sample. The sooner scientists recover a meteorite, the more pristine information it can preserve. That is especially true for carbon-rich meteorites, which may contain fragile organic compounds and minerals altered by water. Sutter's Mill belongs to the gentler side of this top 10 list. No destroyed city, no flattened forest, no crater field, but a real object from space. A fireball, a recovery, a connection to the deep past. It reminds us that space rocks are not only future threats. They are also scientific samples delivered for free if we can find them quickly enough. Each one is a messenger. Some messages are violent, some are quiet. Sutter's Mill whispered about the early solar system. Number 5 is 2018, LA. On June 2, 2018, a small asteroid was discovered by the NASA-funded Catalina Sky Survey. It was faint and estimated to be only about 2 meters across. Astronomers quickly determined that it was on a collision course with Earth, and only hours after discovery, it entered the atmosphere over southern Africa and disintegrated. NASA's Jet Propulsion Laboratory described it as small enough that it was expected to safely break apart in the atmosphere. This event was not important because it was destructive. It was important because it was seen before it arrived. That is the future of planetary defense. Find the object, calculate its orbit, predict the impact, warn if necessary, recover fragments if possible, learn from the event. 2018. LA exploded over Botswana, and later searches recovered meteorites. Scientific work connected the recovered material, called Metopipan, to asteroid 2018 LA, and studied its properties, orbit, and possible origin. A 2-meter asteroid is not a global threat. Most objects of that size burn up or explode high in the atmosphere. They may create a bright fireball and loud sounds, but they are not city killers. Still, 2018 LA matters because it shows both our progress and our limits. We found it only hours before impact. That was enough, because it was small and harmless. But what if it had been 20 meters wide? What if it had been 50? What if it had been larger, dark, and approaching from the direction of the sun, where ground-based telescopes struggle to see? This is where the calm story becomes serious. Planetary defense depends on warning time. If an asteroid is found decades before a possible impact, humans may be able to deflect it slightly, enough to make it miss Earth. If it is found years before, options still exist. If it is found days before, evacuation may be possible for a small impact zone. If it is found hours before, there may be almost no time to respond except to warn people not to stand near windows, not to look for the flash through glass, and to prepare for a possible shock wave. Chelyabinsk showed how important that is. Most injuries there came from broken glass after people saw the bright flash and went to windows. A warning of even a few minutes could matter. A warning of hours could matter greatly. 2018. LA was harmless, but it was a rehearsal. A small rehearsal for the much larger question. Can we see the next dangerous one before it sees us? Number 4 is 2008 TC3, also known through its recovered meteorites as Alma-Ata-Sita. On October 6, 2008, astronomers discovered a small asteroid in space. They calculated that it would strike Earth the next day. On October 7, it entered the atmosphere over Sudan and exploded high above the Nubian desert. Later, researchers and students recovered hundreds of meteorite fragments. This was a historic first, the first time an asteroid was discovered in space before its predicted impact, and then meteorites from that object were recovered on the ground. The recovered stones, called Alma-Ata-Sita, turned out to be unusually diverse, with many different meteorite types represented among the fragments. Again, the event was not devastating, but it was revolutionary for asteroid science. Before 2008, TC3, meteorites were usually studied after they fell, with their original space orbits unknown or uncertain. Here, scientists had both, the object's orbit before impact and the physical meteorites after impact. That meant they could connect telescope observations of an asteroid in space with laboratory analysis of its fragments on Earth. The object was small, only a few meters across. It exploded in the atmosphere. No city was destroyed. No crater was formed. But scientifically, it was a bridge between asteroid astronomy and meteorite science. It also showed that small impactors can be found before impact, if we are lucky, and if the Sky Survey catches them in time. What if 2008 TC3 had been much larger? The difference between a harmless airburst and a disaster is not merely whether something hits Earth. It is size, speed, angle, strength, composition, and where it arrives. A small object over a desert becomes a scientific opportunity. A larger object over a city becomes an emergency. A still larger object over a region becomes a catastrophe. The atmosphere is protective, but it is not absolute. It filters small material constantly. It breaks up many incoming bodies. But for larger space rocks, the atmosphere becomes part of the explosion. The incoming energy is converted into heat and blast. The rock may disappear. The damage may still arrive at the ground. 2008 TC3 was safe. But it points toward the future, a world where dangerous objects are discovered before impact, not after the flash. Number 3 is Caracas. On September 15, 2007, near the village of Caracas in Peru, close to Lake Titicaca and the Bolivian border, a meteorite struck the ground and made a fresh crater. The crater was about 13 to 13.5 meters wide and several meters deep. This was unusual. Most stony meteoroids of modest size break apart high in the atmosphere. By the time fragments reach the ground, they are often slowed and scattered. They may make small pits or simply land as meteorites. But Caracas arrived with enough speed and cohesion to blast out a noticeable crater in soft ground. The event startled local people. Reports described a sudden impact, a crater, disturbed water and soil, and villagers later reporting illness after approaching the site. The exact cause of those symptoms has been discussed, but the impact itself was real, and the crater became a rare modern example of a small meteorite making a fresh impact scar. Caracas is the kind of event people often imagine when they hear the word impact. A rock from space. A strike on the ground. A crater. A shocked local community. But even here, the scale is important. A 13-meter crater is dramatic, but not city-ending. It could kill anyone nearby. It could damage buildings if it struck a village directly. It could contaminate local water or soil with disturbed material. It could cause panic. but it was not a regional disaster. Still, Caracas helps us understand the difference between airbursts and ground impacts. A space rock can explode in the sky, leaving no crater but causing a wide shockwave. Or it can survive to the ground, making a crater but affecting a smaller area. The most dangerous events depend on both. A strong iron object may reach the ground more easily. A fragile stony object may explode in the air. An airburst can spread energy over a wide region. A ground impact can concentrate energy in one place. Caracas was a ground impact story. A small crater, but a real one. If a Caracas-type object hit the center of a town, the result could be deadly locally. A building could be destroyed. People nearby could be killed or injured. But the threat would remain limited. The danger is intense at close range, not global. That makes it different from the next objects on the list, because now we move from local impacts to events large enough to affect landscapes and cities. Number 2 is the Cicote, Alin meteorite fall. On February 12, 1947, an iron meteoroid entered the atmosphere over the Cicote Alin Mountains in southeastern Russia. It broke apart violently and rained iron fragments over the ground. Many pieces survived the fall, and the total recovered mass was enormous, with more than 20 tons of fragments reported. The event created a strewn field and many impact pits and craters. This was one of the most spectacular meteorite falls in recorded history. Witnesses saw a brilliant fireball brighter than the sun. A trail stretched across the sky. Explosions were heard. Then fragments of iron struck the ground, punching craters into snow, soil, and forest. Unlike Chelyabinsk and Tunguska, Cicote, Alin involved many surviving meteorite fragments hitting the surface. It was not only an airburst, it was a shower of iron. Iron meteorites are tough. They can survive atmospheric entry better than fragile stony bodies. They may fragment, but the fragments can remain large and hit the ground at high speeds. Cicote. Alin showed what happens when a strong metallic object breaks into a storm of falling masses. No major city was beneath it. That mattered. Had Cicote Alin happened over a populated area, the falling fragments could have caused serious local destruction. Large iron pieces could have smashed through roofs, roads, vehicles, and buildings. Multiple craters across a town or city would have created chaos. Even smaller fragments falling at high speed can be deadly, but it still would not have been the same as Tunguska. Cicote Alin's danger was in the fragment shower. Tunguska's danger was in the blast wave. Chelyabinsk's danger was in the shock wave over a populated region. Each space rock teaches a different lesson. Cicote Alin teaches that not every dangerous event is a single crater. Sometimes the sky breaks into pieces. Imagine standing in a snowy forest in 1947 and seeing daylight erupt across the sky. A fireball tears overhead, then splits. Seconds later come the sounds, detonations, rumbling, impacts. Iron falls from the heavens. Not metaphorical iron. Real metal from space, older than humanity, striking the ground hard enough to gouge craters. There is something ancient and elemental about it. The sky becomes a forge, then a battlefield, then a museum. Because the fragments that fell at Cicote Alin are now studied, collected, and displayed. They are dark, metallic, often twisted and thumbprinted by atmospheric heating. They are beautiful in the way. Dangerous things can be beautiful after danger has passed. But if the fall had been over a city, beauty would not have been the first word. It would have been impact. Number 1 could only be Tunguska. On June 30th, 1908, over a remote region of Siberia near the Podkamenaya Tunguska River, something entered Earth's atmosphere and exploded in the sky. The blast flattened about 2,150 square kilometers of forest. Estimates of the energy vary widely, but it was enormous by human standards. No confirmed impact crater was found, which supports the interpretation that the object exploded in the atmosphere before reaching the ground. NASA describes Tunguska as the largest asteroid impact event in recorded history and notes the extraordinary area of forest damage. This is the event that sits above the others because it shows what a medium-sized space rock can do without ever making a crater. The Tunguska object was likely tens of meters across, not kilometers, not dinosaur-ending, not large enough to cause a global extinction. And yet it flattened a forest over an area larger than many major cities. Trees were knocked down in a vast radial pattern. Animals died. Eyewitnesses described fire in the sky, heat, shock, and thunderous sound. Because the region was remote, human casualties appear to have been few or uncertain, with some accounts suggesting possible deaths, but not the mass casualties that would have occurred over a city. This is where the imagination becomes uncomfortable. What if Tunguska had happened over London, over Paris, over New York, over Moscow, over Tokyo, over Mumbai, over any dense modern city? A Tunguska-level airburst over a major city would not need to make a crater to become a disaster. The shockwave could flatten or severely damage buildings over a wide region, depending on burst altitude and energy. Windows would shatter across enormous areas. Fires could begin. People outdoors would be exposed to blast, heat, debris, and collapsing structures. Emergency systems would be overwhelmed. Hospitals, roads, communications, and power infrastructure could fail in the damaged zone. If it exploded over Manhattan, the financial district, Midtown, or surrounding boroughs could experience catastrophic destruction depending on the burst location and altitude. Glass towers would become dangerous, not because the rock hit them directly, but because pressure waves would turn windows into flying blades. Bridges, tunnels, and underground systems might be disrupted. Millions of people live and work within ranges that could be affected by a large airburst. If it exploded over London, historic buildings, modern glass offices, dense neighborhoods, rail stations, and bridges could all be affected. The blast would not respect the age or meaning of the city. It would simply move outward as pressure. If it exploded over Paris, the same would be true. Windows, roofs, monuments, apartments, narrow streets, crowded public spaces. A beautiful city built over centuries could be wounded in seconds. If it exploded over Tokyo or Mumbai, the sheer population density could turn a natural event into a humanitarian catastrophe. This is not because Tunguska was planet-ending. It was not. That is the key. A Tunguska-sized object is not the end of humanity, but it could be the end of a city center. It could kill many people if it arrived in the wrong place. It could cause economic, psychological, and political shock far beyond the blast zone. Tunguska is frightening because it is not ancient. It happened in 1908. That is recent. The world had newspapers, railroads, electricity, telegraphs, cities, and cameras. Yet a cosmic explosion flattened a remote forest before humans had any meaningful warning system. If the same object had arrived a few hours later or earlier in Earth's rotation, it could have exploded over a very different place. That is the unsettling truth. Earth's rotation saved cities by chance. The object did not aim for Siberia. It simply met Earth there. Tunguska also teaches that craters are not the full record of danger. If scientists searched only for craters, Tunguska might seem invisible. No great bowl in the ground, no central impact scar. The object disappeared in the atmosphere, but the forest told the story. The trees were the crater, a crater made of absence, a blast pattern written in wood. The atmosphere protected Earth from a direct impact, but it did not remove the energy. It converted the impact into an airburst. That is why Tunguska remains the defining event for planetary defense. It is not the largest impact Earth has ever known. It is not the most recent dangerous airburst. but it is the clearest warning from recorded history that a space rock only tens of meters wide can cause regional devastation. Then, more than a century later, Chelyabinsk reminded us again. Chelyabinsk is not number one in raw energy compared with Tunguska, but it is perhaps the most important modern warning. On February 15, 2013, a house-sized asteroid entered the atmosphere over Russia near Chelyabinsk. NASA reports that it entered at over 11 miles per second and exploded about 14 miles above the ground, releasing energy equivalent to roughly 440,000 tons of TNT. The shockwave blew out windows over a wide area, damaged buildings, and injured more than 1,600 people, mostly because of broken glass. The Planetary Society describes damage to thousands of buildings across multiple cities, with many people injured after seeing the flash and moving toward windows before the shockwave arrived. Chelyabinsk is the event that belongs in every modern conversation about asteroid risk. It was not predicted. It came from the direction of the sun, making it difficult for ground-based telescopes to detect before impact. It was only about 20 meters across. It did not make a city-sized crater. It did not kill thousands. And yet, it injured more than 1,000 people. That is what makes it so important. It showed that a relatively small asteroid can cause widespread urban damage without hitting the ground as a single large object. The sequence was simple and dangerous, a brilliant flash. People looked toward it. The shockwave arrived later. Windows shattered. Flying glass caused injuries. If the object had been larger, lower, stronger, or over a denser city center, the outcome could have been far worse. If schools, offices, and apartment blocks were directly under the strongest blast region, casualties could have been higher. If the airburst occurred lower, pressure damage might have been more severe. If emergency systems were unprepared, panic and confusion could have added to the harm. Chelyabinsk was not humanity's destruction. It was humanity's warning. And it happened in the age of cameras. Dash cams captured the fireball from many angles. Videos spread around the world. For perhaps the first time, millions of people could watch a significant asteroid airburst almost as it happened. The event was not a story told by a few witnesses in a remote forest. It was visible, recorded, replayed, analyzed. The sky had entered the internet age. Chelyabinsk also revealed a practical lesson for public safety. If you see an unexplained bright flash in the sky, do not rush to the window. Move away from glass. The shockwave may arrive later. That simple action could prevent injuries in future airbursts. In that sense, Chelyabinsk gave us not only science, but instructions. Now, after these 10 events, the question becomes larger. How bad could a future impact be? The answer depends on size. Tiny particles burn up harmlessly every day. Objects a few centimeters across can create bright meteors. Objects a meter or two across can make spectacular fireballs and sometimes drop meteorites. Objects around 20 meters across, like Chelyabinsk, can explode with enough force to damage buildings and injure people over a wide area. Objects tens of meters across, like Tunguska, can flatten forests or devastate a city if the burst occurs over one. Objects hundreds of meters across could cause regional destruction and severe climate effects. Objects around a kilometer or more become global concerns. And objects several kilometers across are civilization, threatening, or worse. But the good news is that larger objects are easier to find. Astronomers have discovered and tracked many large near-Earth asteroids. The greatest unknown danger now often comes from smaller but still dangerous objects, tens to hundreds of meters wide, dark, fast, and potentially hidden by sunlight or incomplete sky coverage. This is why planetary defense matters, not because disaster is likely tomorrow, but because the consequences of rare impacts can be enormous. NASA's DART mission showed one method of asteroid deflection, deliberately crashing a spacecraft into an asteroid moonlet to change its orbit. That test, performed on Dimorphos, was not a response to an actual threat, but a demonstration that human technology can alter the motion of a small asteroid under the right conditions. The earlier we find an asteroid, the less we have to change its path. A tiny nudge years in advance can become a miss instead of an impact. But if we find it too late, deflection may be difficult or impossible. Then the goal becomes warning. Evacuate the region. Move people away from glass. Protect infrastructure. Prepare emergency services. Understand whether the event will be an airburst, a fragment fall, or a ground impact. Every event on this list teaches a piece of that system. Ensisheim teaches that humans have watched stones fall from the sky for centuries. Murchison teaches that meteorites carry chemistry from the early solar system. Peekskill teaches that space rocks can touch ordinary lives in strange ways. Sylacauga teaches that meteorites can even strike people, though rarely. Sutter's Mill teaches the value of fast recovery and scientific study. 2018, LA teaches the importance of detecting incoming objects before impact. 2008, TC3 teaches that prediction, impact, and recovery can connect astronomy with meteorite science. Karankis teaches that small ground impacts can still make real craters. Sikote, Alan teaches that iron fragments can rain down and scar the ground. Chelyabinsk teaches that airbursts over populated regions can injure many people. And Tunguska teaches that a city-sized disaster does not require a city-sized asteroid. The object can be only tens of meters across. The damage can still be enormous. But this story should not end in fear alone. Earth is struck constantly, but most impacts are small. The atmosphere is a shield. The oceans and unpopulated regions cover much of the planet. Large impacts are rare. And unlike earthquakes or volcanoes, asteroid impacts are, in principle, preventable if we detect them early enough. That makes them unique among natural disasters. We cannot stop a hurricane from forming. We cannot stop an earthquake from beginning. We cannot stop a volcano from existing. But a dangerous asteroid found early may be moved. Not with panic, with time, physics, careful tracking, international cooperation, and engineering. The sky is not empty, but neither are we helpless. As the night grows quiet, imagine Earth from space, a blue world moving through darkness. Around it, tiny grains burn up as meteors. Larger stones pass by unnoticed. Some enter the atmosphere, most vanish, a few survive. A few leave scars, and rarely, very rarely, something larger arrives with enough energy to remind us that Earth is part of a moving solar system. The stars above us are calm most nights, but the calm is not separation. The calm is motion. Earth travels around the sun at high speed. The solar system contains ancient debris. Asteroids cross orbits, comets shed dust. Meteor showers return, fragments fall. Most are harmless, some are beautiful, some are scientific gifts. Some are warnings. The top 10 space rocks in recorded history are not only a list of impacts, they are a list of lessons. A stone in a field, a chemical treasure in Australia, a car struck in New York, a woman bruised in Alabama, fragments in California, a predicted asteroid over Botswana, a recovered asteroid over Sudan, a crater in Peru, iron rain in Russia, glass injuries in Chelyabinsk, a flattened forest in Tunguska. Each one says the same thing in a different voice. The universe is not far away. It reaches us, sometimes as dust, sometimes as light, sometimes as stone, sometimes as shock, and sometimes, if we are wise, as warning. For now, the sky remains quiet, the atmosphere holds, the stars shine, Earth continues its long path around the sun. And somewhere out there, small rocks drift in darkness, following ancient orbits, waiting for gravity, time, and chance to decide their paths. Most will miss us. Most that arrive will burn away. Some will become meteorites in fields, deserts, forests, rooftops, and rivers. And a few, once in a long while, will remind humanity to keep watching the sky.